Okay, this is lesson 1.5a, the inverse function and its properties. Part A will be the inverse function graphically, part B will be algebraically. So first off, what is an inverse function? Well, an inverse function reverses or undoes the original function. So think about the expression sine A equals 0.5. If we wanted to figure out what A was, the angle, we would have to use sine inverse. So if we wanted to find A, we would have to use sine inverse of 0.5, and that would tell us what A is. Sine and sine inverse are inverse functions because they reverse the original function. So if I use this machine as an example, if we have an x and we feed it into a function, we get out a y. What we put in is called the domain, and what we get out is called the range. If we had a machine that would undo the original function, and we called it f inverse of x, the -1 exponent means inverse, just like it did up here in sine inverse. If we put the y into our inverse function, what we would get out is an x. But in this machine, the input is still called the domain, and the output is called the range. I was going to write output. So here's an example as a function as a machine, and here's the inverse function. Whatever you get out of the original function, the output y, if you were to feed it back into the inverse machine, you would get back out the original input. And as we notice here, the x's are the domain and the y's are the range, and that's for our original function. But in the inverse function, the y is the domain and the x is the range. So the x's and y's flipped. The domain and range flipped. And that's what an inverse function is. So a function f of x may or may not have an inverse function. It will always have an inverse relation, but it may not be a function. F of x will have an inverse function if it passes the horizontal line test. That means if you take the graph of the original function and draw horizontal lines across it, and it only hits once, the inverse will be a function. Also, the inverse function will be a reflection of the original function in the line y equals x, the oblique line. And I'm going to show you what that looks like down below. Essentially, what we're doing is we're switching the values of x and y. And that means the domain of the original becomes the range of the inverse, and the range of the original becomes the domain of the inverse. And here's what it looks like as a point. If you had a point x, y, in the inverse function, the point would have the coordinates y, x. So, for example, if we had this figure. This is a triangle, and it has 3 points. -4, 0, -1, 2, and 0, -2. The domain of our figure is these 3 points. I've connected them to make the triangle. Let's just assume it's just these 3 points. That's the actual function. So I connected it so you can kind of see how it looks when you find the inverse. But in the domain, we have -4, -1, and 0. And in the range, we have 0, 2, and -2. When we flip them, we should have the opposite. So what we're doing is we're flipping x and y, and that will reflect it along this line y equals x. To graph the line y equals x, think about your y equals mx plus b. 1x plus 0, 0 is the y-intercept, and the slope is 1. So over 1, up 1, over 1, up 1, over 1, up 1 gets you all the points on the line. That's what I've done. I've just graphed our line to show you that all we're doing is we're going to reflect this over the line. Reflecting is like mirroring. So here we go. We're going to flip some coordinates. I need a different color here. What other color? I can use a pencil. Our first point is -4, 0. That would become 0, -4. We're flipping x and y. And -1, 2 would become 2, -1. And 0, -2 would become -2, 0. And if we connect them, we can kind of see what happened here. Again, connecting them is just so you can see what it looks like. We're not actually going to always connect our dots unless we have a normal function. This is just an object. And here we go. Here's our triangle, original triangle. We'll call it f of x, even though it's not a function. And our inverse. And what you can see is the points have just been reflected over the line. The distance of this point to this line is the same as this point to this line. Same as this point to this line and that point to that line. This point to the line, that point to the line. They're just on opposite sides. That's a reflection. What we've done is we've come up with the inverse. We've reflected it. So let's see what that looks like for some of our parent functions. There's 6 on this sheet. I'm going to do 2, and I'm going to get you to try to do the other 2. But here we go. It's hard to see the scale, but if you look closely, you might be able to see it, and if not, I'll kind of try to help out. Basically, the scale is every box is half a unit, so every 2 boxes is 1 on all the scales, I believe. Yes, all the scales. What we're going to do here is for each parent function, we're going to determine whether the inverse function exists using the horizontal line test. We're going to sketch the inverse of each function, and we're going to state the domain or range of each inverse. So here we go. We've got our linear function, y equals x. Wait a second. That was the line we were reflecting over. So let's think here. We've got a couple points on this line. I'm going to pick those points. And I go with these points, this point, and we'll go one a little bit further down, say this point. And if I were to switch the coordinates, maybe we'll get a couple more. That one. If I were to switch the coordinates, we would say, let's look at this one. This is 1, 1. So if I switch 1 and 1, I get 1, 1. This is 0, 0. If I switch 0, 0, I get 0, 0. Switching the x's and y's doesn't actually change anything. -1 and -1 still gives me -1, -1. What's going on here? Well, all these points are actually on the line, so reflecting it doesn't change the graph at all. So if we were sketching the inverse of this function, we've already graphed it. F of x, if we call the original f of x, is the same as the inverse. This is an example of a self-inversing function. If an original function inverses and ends up being the exact same line, or exact same curve, exact same graph, it itself is its own inverse. And there's a few examples of that in math. And you'll see a couple more maybe as you complete the sheet. But this is definitely one of them. The y equals x graph, the linear function, is its own inverse. So in terms of domain and range, the domain of the inverse, well, it'd be the domain of the original too, because, well, it is its own inverse. Since it continues all the way to the left and the right, I'm going to draw arrows on here to make it clear. Anytime a graph goes off the graph, a function goes off the graph, you can assume it continues in that direction forever. The domain would just be that x belongs to real. There's no restrictions on the x, and same with the y, up and down. We skip the first part by accident. Determine whether the inverse function exists using the horizontal line test. Usually we do vertical line tests to see if the function if the relationship is a function, and the linear function is indeed a function. If we do the horizontal line test, we still only hit the graph once by drawing horizontal lines across. So that means the inverse is a function. But since it's the same as the original, we already knew that. All right, that's the first one done. Quadratic, let's try a quadratic. I'm going to take a couple key points here so we can flip them. 0, 0, 1, 1, 2, 4. -2, 4, -1, 1. There we go. Now we got 5 key points. Let's switch x and y of these points and get new points. 0, 0, if we flip x and y, 0, 0 is the new point. 1, 1, if we flip x and y, 1, 1 is the new point. Uh-oh, what do we got going here? Maybe the same as last time, or maybe not. 2, 4. If we flip 2 and 4, we get 4, 2. Aha, a new point. 4, 2. There we go. And this part is the first branch, or the one side of the parabola. Let's try the other side. -1, 1. If we flip that, we get 1, -1, which would be 1, -1. And if we flip this point, -2, 4, we get 4, -2, 4, -2. And if we connect those, we get this branch. We keep skipping the first step. Determine whether an inverse function exists using the horizontal line test. Well, now looking at the inverse, we can kind of tell that, well, this isn't a function because it doesn't pass the vertical line test. But if we look at the original and do a horizontal line test, it would hit here and here. Or if we did it down here, it would hit here and here. So it's not a function. So if we call the original f of x, x squared, this would be our inverse function. And f inverse is not a function. And it's not a function, you can say, for two reasons, actually. F of x fails the horizontal line test, or f inverse of x fails the vertical line test. Either one would work. Let's try domain and range. Domain. Remember, we're doing domain and range of the inverse. So let's look at the inverse's domain. Well, there's no graph over on this side. The graph seems to start here and only go this way. So it looks like it's starting at 0 and going all the way to the right and on forever because we have arrows in this direction. So it looks like our x's, since we're connected with a nice curve, belong to real such that x has to be greater than or equal to 0 because it's starting at 0 and there's a point there at 0, so 0 is in the domain. And our ranges, well, we're going all the way up and continuing up. We're connected all the way through the middle, and we're going down and on forever. So the y's actually don't have any restrictions. Y belongs to real. And if we draw that y equals x line on here, you can see that it's a reflection. This wasn't part of the question, but I'm going to do it anyway so you can see it. We got a line that goes right up through here. Try to get it as accurate as possible. There we go. I guess I could have used a ruler. But if this is our y equals x line, you can see that it's just a reflection over that line. All right. There's 4 more here that I want you to take a shot at. There's the reciprocal graph, the absolute value graph, the square root, and the discrete points, which means just graph these points, flip x and y, don't connect the dots, and see if the inverse is a function. You can try that now and then check your answers on the website. Thanks for watching, and I'll see you next time.